this. Linearization is just the idea that when you take a derivative of something, you get its tangent line. Well, that tangent line is a good representation of the function on a very small interval. It's the idea that if you take a function and zoom in far enough on it, if the function's derivative exists at some point that you're zooming in around, eventually the function will begin to resemble the tangent line almost exactly. And you can do that with any function you want where it has a derivative, graph it and zoom in and zoom in and zoom in, and eventually it just begins to look like a straight line, right? It just begins to look like the tangent line. And so the idea of linearization is just using that tangent line to approximate the value of the function on a very small interval. And so we did this last year for those of you that were in my class last year, but we did not attach to it this idea of the approximation. So we're going to do this because they do ask about this in BC. Is the accuracy of your approximation can always be found by taking the actual value and subtracting your approximation, which we call L of A, right? By finding our, this should not be A, sorry, those should be X's. By taking the approximation at X and subtracting from it the actual value of the function of X. So we want to be able to do these accuracy calculations as well. So our linearization function is just f of a plus f prime of a times x minus a, where a is what we call the center of approximation. So if I'm looking for, let's say, the square root of 26, the center of approximation will be a equals 25, because that's the value that is very close to 26 that we know how to take the square root of it. And so x would be 26, and our function f of x would be the square root of x. Good or no? These are the things we'd plug in. We'd have to find f prime, and then we would evaluate it all out. Everybody good with the idea of using this tangent line approximation, this linearization, to approximate something? Oh, look, there it is, square root of 26. So let's do this. Let's say we just said f of x is square root of x, and we should probably find f prime of x. What's f prime of x? Should be 1 over 2 root x. So we should be able to use all this information that we just said to approximate the square root of 26. So we will say that the square root of 26, that's f of 26, which should be approximately equal to the linearization at 26, which is f of a, so square root of a, plus f prime of a times x minus a. And we just plug it all into the formula and get an answer. So root 25 is 5. This is a 1 times 1/10, so 5 plus a 10th, or 5.1. And you have a calculator in front of you. If you don't, go get one. We should be able to approximate the square root of 26 on the calculator and see how accurate our approximation actually is. So I'm going to just go ahead and do that without having you do it. It's 5.099019514. And if we take our approximation value, we end up getting 9.805 times 10 to the negative 4. And so what we would then say is this is off by, these 9.8 times 10 to the negative 4. So we would say that it has accuracy of 10 to the negative 3, 1 power higher than this is. Right, so we're accurate to 3 decimal points here, basically. We're off by less than 1/1000. Does that make sense?
How many decimal?
Say that again.
How many decimal points do you want us to go to for the actual value?
I mean, you can cut it off shortly after where it diverges. So, I mean, 5.09901 would be fine.
Okay, thank you.
Yeah, so to wherever, like, at 5.099, this would round to 5.1, right? If I go one more decimal, though, 5.09901, let's say, we'll leave it. I mean, that would be good enough. Just so long as what you get is still going to give you this nice little scientific notation thing that you get when you plug it into your calculator. I mean, to be safe, just put the whole thing in, but. All right, let's do another one. So we're doing cosine of x, and we're going to center it at x equals pi over 2 and approximate it with the cosine of 1.71, because pi over 2 is pretty close to 1.71. So f of x is cosine x. What's f prime of x?
Negative sine x.
Oh, good. Somebody remembers how to take a basic derivative. Good. All right. And our a value is pi over 2, and our x value is 1.71. And so if we go in here, what do we end up with? We end up with the cosine of 1.71 should be approximately equal to L of 1.71, which is f of a, so cosine of pi over 2, plus f prime, negative sine of pi over 2, times x minus a. And cosine of pi over 2 is 0, and sine of pi over 2 is 1, so this is just negative 1 times this. So this becomes pi over 2 minus 1.71. And what does that approximate out to be? This time you have to do it on your own.
Negative 0.13920. Do you want to go further? Or?
Yeah, sure. Let's go further.
After that is 36732.
36732. Cool. And so then if we want to know how accurate that answer is that we got, we just go back in and we say, all right, let's take the actual cosine of 1.71 and subtract this. And take the absolute value. And what does that come out to be?
$4.49 times 10 to the negative 4, I believe.
Great. So 4.49 times 10 to the negative 4 tells us that we are off by 0.000449, which means that we are accurate to 3 decimals, 10 to the negative 3 accuracy. Good or no? I'll take that as a yes. All right. We can extend this idea not just to simple functions like sine and cosine or square roots or cube roots, but we can do this basically with any function. And we call these differentials when we do it with just regular old functions in general. We sort of take the dy dx, which we know is the derivative, f prime, and we split the variables of it. We take dx, the independent variable, and our dy, which is our dependent variable, and we just define them as their own specific variables that we can multiply by dx and say that a small change in y, dy, is equal to f prime, the derivative of f, times a small change in x. And so this is effectively doing the same thing. It's treating the dy dx only as a slope and saying that small change in y is equal to the derivative times the small change in x. And so we should be able to apply this to any function that we want. For example, a function like x to the fifth plus 37x. So if I say x is going from 1 to 1.01, and I want to know about how much does y change, what's the differential dy, all we have to do is say dy should be equal to the derivative of this, which is 5x to the fourth plus 37, times our dx value. And to find the actual value of dy, we get 5 times 1 to the fourth plus 37 times that 0.01. And what does that come out to be? Looks like that's 0.42. And so we would say that as x goes from 1 to 1.01, the y value increases by about 42/100. Does that make sense?
Yes.
Yes.
All right, spectacular. Let's do another one of those. In fact, why don't you do this one on your own? Ready, go. So hopefully we got dy equals, using the chain rule, right? 3 cosine 3x dx. And so dy was equal to 3 cosine 3 pi times negative 0.02. And what was the cosine of 3 pi?
-1.
-1. So this is -3 times your negative 0.02. You just get 0.06. So that's about how much y changes. Good or no?
Good.
All right. We can even do this with implicitly defined equations. So now we just end up with dx plus dy equals, and then this will be using the product rule, 2x dy plus 2y dx. And then we'll just plug in all of our values. The only problem with this is when we plug in all of our values, in fact, let's solve for dy first, actually. So dy minus 2x dy equals 2y dx minus dx. And our dy is equal to 2y minus 1 times dx over 1 minus 2x. And what's the problem here? When we try to plug things in, we are missing. What are we missing? We're missing a value for y. So remember, all we have to do to find that missing value of y is just plug in x equals 2, 2 plus y equals 4y. And what do we get? We get y equals And we get y equals
2/3.
2/3. So we'll plug it all in. dy ought to be 4/3 minus 1 times our dx all over 1 minus 4. And we can simplify that out if we wanted to. We got a third and we got another -3 down there. So what is that? What does that come out to be?
-1/120th.
You guys agree with that?
-1/180th.
Sorry, say that again.
Sorry, I messed up. -1/180th.
You guys agree with that?
Yeah.
Yeah, that sounds better to me, right? That's a 900 in the denominator, right? 5 over 900. Write the 500s out. Any issues with that or no? All right, so now what we're going to do is we're going to use the idea of differentials to approximate the change in some actual physical object that we're going to have, like a circle, for example. And we're going to introduce a couple of new ideas here called relative change and percentage change. Hold on one second. All right, so we're going to take a circle and we're going to increase its radius from 5 to 5.1 meters, and we want to estimate the increase in this circle's area. So if the area of the circle is pi times the radius squared, then the change in the area ought to be 2 pi r dr. And so we can find that the change dA in the area is about 2 pi times the original radius of 5 times the change in the radius of 0.1. And so what does that give us? That gives us a change of about pi meters squared. Everybody good with that part of it?
Yes.
Okay. So then what we need to do is you're going to be asked this year to find what we call the relative change and what we call the percentage change. So the relative change is just how much it changed by, which was what? How much did it change by? About pi, right? Divided by f of a, that's f of our original amount. So our original amount was 5 meters, so f of a is the original value, which would be 25 pi. Right? Pi times that radius squared. Good? And what does that give you? It gives you 1 over 25, or a relative change of 0.04. So relative change is always the how much it changed by the original amount. And then we will also be asked about the percentage change, and your percentage change is just that multiplied by 100 to turn it into a percent, 4% change, about 4% change. Good or no? So relative change, how much it changed divided by the original amount, and then percentage change is the relative change times 100. You're going to need and want to know those. Any questions or issues with that? All right. So let's suppose the Earth was a perfect sphere and, not flat like we all know that it really is. But well, we'll pretend for our sake here that it's a perfect sphere with a radius of 3,959 miles. So we measured it, but we might have been off by about 1/10 of a mile when we measured that radius. So we want to know how much of an effect on the surface area of the Earth would that 0.1 miles that we might have been off by, how much would that affect the surface area? So first thing we need to do is we need to write out an equation for the surface area of a perfect sphere. Right? What's the surface area of a sphere?
Four pi r squared.
4 pi r squared. And so a small change in the surface area, ds, would be 8 pi r dr. And so we'll say that that ds value is 8 pi times our original radius. What was our original radius? Should have been 3,959, right? Times our error. How much were we off by, maybe? How much was the change in the radius that we might have missed? 0.1, right? And so what do we end up with that for that?
$9,950.05.
9,950.05. You're going to round to 2 decimals. Not going to round to 3 decimals like the AP test always wants.
Right. Then there's a 2.
Right, good. Okay, so this means that we could have been off if we calculated it 3,959 miles, but we said, well, where our error is plus or minus 0.1, well, then we might have been off by 9,950.052 square miles. And what if I asked you for the relative error, the relative change that we would have? We should take our amount that it was off by, 9,950.052, and divide that by the original amount that we would have gotten. What would the original surface area be? It would be 4 pi times our radius squared. And so that's our relative error. And what is our relative error if our error in measurement was 0.1 miles?
5.052 times 10 to the negative 5th.
5.052 times 10 to the negative 5th. Okay, and what if I asked you for the percent error? That would be?
Yes, 5.052 times 10 to the negative 3rd percent.
Right. Easy enough. Or we could say 0.005052%. So 9,950 square miles seems like quite a lot, but in terms of the how much we're really off by in a percentage, it's not very much at all, really. Good or no?
Good.
Great. Hopefully this should be fairly easy so far. So let's suppose we are trying to calculate the surface area of a sphere to within 1% of the value that it actually has. So that would mean that we want our percentage change or our percentage error to be less than 1%, right? Percentage error would be less than 1%, which would tell us what about the relative error? It should be less than 0.01, right? Should just be less than the 1 divided by 100. Yeah or no? You guys all
Yeah.
agree with? Yeah, okay, we agree with that. Good. All right. So now let's go in and actually work with the surface area a little bit. So the surface area we know is 4 pi r squared. And that would tell us that ds, the error on the surface area, should be 8 pi r dr. And so we're looking at how accurately should we measure the radius, which means we're really looking for a dr value. But we're given a relative error on the surface area of 0.01 or being less than 0.01. So what's relative error on the surface area equal to?
Eight pi r dr over 4 pi r squared.
Right, it's equal to the change in the surface area over the actual surface area. So I need to divide both of these by f, or divide them both by 4 pi r squared. So this would be 8 pi r dr over 4 pi r squared. We want to be less than 0.01. So we should be able to simplify that down fairly nicely. What does it give us? It gives us 2 dr over r is less than 0.01, which tells us that dr needs to be what? Less than, I guess I should probably put equals, less than or equal to here.
0.005 r.
0.005 r. So the relative error on the radius would need to be 0.005 of the actual radius, or we could say 0.5% of the true value of r. So if we want to make sure that our surface area is within 1% of the actual value, that means we need to measure the radius to within 0.5% of accuracy. Does that make sense or no?
Yeah, that's cool.
Everybody good? Any questions on that? All right, let's take a look at another one here. You guys want to try and work through this one on your own or no?
Yes.
All right, Max says that you also want to. So I'll give you guys a minute or two to see if you can work through this one, and then we'll go through it together. Ready, go. All right, so we're looking at a 10% increase in R and how that affects the volume, right? So what does a 10% increase in R look like just in terms of dr? Dr ought to be a change by 0.1 of R. Is that what you guys used for your DR value?
Yes.
Oh, perfect. Okay. And then we were looking for dV to start with here, right? So dV should be 4, and K is just a constant, 4KR cubed dr. And what should we do from there? What do you guys do from there?
dr is 0.1 r, so plug that in.
Okay, so dV gives us 4 times K times 0.1 times R to the 4th. Okay. So that tells us what dV is. But what are we looking for? We're looking for
dV over V.
dV over V, right? So we need to looking for how much does that change affect it. And we were given a percent change originally, so we should probably give a percent change in the end. So if we divide this by V, that'd be like dividing this by KR to the 4th. Right? And what does that give us? That gives us that our relative change, dV over V, I'll just write that as relative change in V now, is what?
0.4.
Just right. Which tells us that it is a what percentage change? Should be 40% change in volume. Good or no?
Fascinating.
Is it? This is one of my least favorite topics of the year. When they try to apply math to things, that's when math gets boring. Applying it to science. Ugh. All right. Let's see here. Let's do, I guess, one last one of these, huh? You guys want to do this one on your own? Okay, cool, good. Do this one on your own. Ready, go. So, we are looking for the depth of the well, right? So we're looking for how much are we off with in terms of S. We're looking for a DS value. So DS ought to be 32 TVT. And what is our timing error? What is our change in the time, or our error on the time? It could be up to 0.1. So we'll just plug in 32 times our actual calculated value times how much we think we're off by. And that tells us that if that stone falls for 2 seconds, about 2 seconds, but we think we might be off by 1/10 of a second, that means that our calculation for the depth of that well ought to be off by maybe at most 6.4 feet. And if the deeper the well is, the larger our error might be, right? So if we're off by 1/10 of a second, but it took 5 seconds to drop, what does that come out to be? Let's see, 16 feet. Cool. Easy or no? So using tangent lines to approximate, and then using that idea of differentials to sort of approximate how much our error might be with our calculations, because sometimes our calculations might not be perfect. Any questions or issues with any of that?
So when it asks how sensitive will your calculations be or something like that, it's asking for the DS or the whatever that value is. Okay.
Yep, it's asking for how much off are you, or how much off could you potentially be if you had a timing error of 1/10 of a second. The difference between that and this is how much does an increase affect the actual value of our our V in terms of percentage. So since we were given this in a percentage, we want to, put it back out in a percentage.
Will like questions on this on quizzes and stuff be a little bit more explicit as to the units and like what our answer should actually look like?
Sure. I could do that.
Or I guess like on the AP test.
Yeah, I mean, they will usually say like, what is the percentage error, or what is the relative error in the volume, or what is the percentage error in the change of the surface area, or something like that. They'll be,
Okay.
should be.
Cool. Thanks.
Any other questions on this?